So now that we've separated our variables into these different parts, we can separate out our Schrodinger equation into 3 separate parts. So we can take our del squared operator and look at just the x part, just the y part, just the z part. So overall, we'll end up with negative h bar squared over 2m, and we'll end up with 1 over x of x d squared x of x dx squared minus h bar squared over 2m, 1 over y of y d squared y of y over dy squared minus h bar squared over 2m d squared z of z dz squared is equal to e. And what I've done here is, missed a z of z here. What I've done here is just moved our wave function, just divided it out on each side. Now, each of these parts has to be equal to a constant, and we'll call each of those, we'll call ex, ey, and ez, kind of each individual part of this. And the total is going to be e. So e will define such that we'll add all of these constants together here. So if we look at just one part of this, let's look at just, say, the x part. We have, yet again, something we've seen before. We have negative h bar squared over 2m, 1 over x of x, second derivative with respect to the x part of the function with respect to x will be equal to a constant ex. And again, our boundary conditions, x of x at x equals 0 and a has to be equal to 0. We've solved this problem already. This is the exact same wave equation that we saw previously. And we end up with the exact same solution as we did for the one-dimensional particle in a box. X of x is equal to some constant a sine nx pi x over a. All right, and nx is equal to 1, 2, 3, etc. And there's nothing different about the y and z solutions. And so we end up with the exact same thing for y of y. We end up with some constant for the y dimension, sine ny pi y over b. So the only thing that changes is which length we're looking at. Ny is 1, 2, 3, dot, dot, dot. And same for the z part. Z of z is some z constant, sine nz pi z over c, where we have now a quantum number for the z dimension as well. And actually, all of these constants here, the normalization is going to be the exact same as it was for the one-dimensional object, for the one-dimensional particle in a box. And so we can say, we know that a of x is going to be square root of 2 over a of y is going to be square root of 2 over b, and a of z is going to be square root of 2 over c. We can combine all of this, and our overall solution, psi as a function of x, y, and z, is just going to be all these multiplied together. We'll get the square root of 8, 2 times 2 times 2, over ABC, that's our normalization constant, times sine nx pi x over a, sine ny pi y over b, sine nz pi z over c. And that is our overall wave function for our system. And then our energies are going to be similar to the particle in a box in the one dimension. E is going to depend on now 3 quantum numbers, nx, ny, and nz. And we'll get h squared over 8m. And then we have our 3 different quantum numbers show up. Nx squared over a squared plus ny squared over b squared plus nz squared over c squared. Okay, and so what we see here is that because of our 3 dimensions, we now have 3 quantum numbers. We can see, and this is generically true when we have sort of multiple dimensions here, the wave functions, we can kind of, when we separate out the variables, the wave functions just multiply together. Right? We essentially have 3 one-dimensional particle in the box wave functions multiplied together to get our final solution, but the energies add, right? If we take those wave functions and multiply them, the energies add together. And so we've kind of combined them into this equation that we have here.